Well, guys, welcome again. I hope you had a good weekend, that you did something productive, that you don't forget mathematics, and that we will see that today your batteries are charged. So, of course, I get the perennial question. Somebody messaged me asking me, so when is the first exam? You have nothing to worry about it. It will be told to you ahead of time. You will not miss it. It will not happen like this. What worries me is that when I give you the first exam, you will find that you don't need to do too much about it. Okay? And I hope you will not feel this way. There is so much more to this class than what you are tested on. So another thing I should mention, I will mention that again once we are there, is that naturally, especially in this setting, people tend to cheat better than they do in the middle of the class. So some people, for example, would post their questions on a website. I cannot guarantee that I will find those questions on the website, but it has happened before that, I can find such things. And not only that, I can find such things, and then through the department, even if it's under another name, I can figure out who that person might have been. Okay, and even if I cannot figure who that person might not have been, you see, I can be rather upset as I put a lot of effort into this class. If I see that that people are just trying to not learn, to escape from it, I will start testing you one by one, starting with the people that, of course, do not come or do not show their faces or don't participate. Those would be the first people that I will test. So I will give 3 questions at that case, right? We'll see how much I will do that. And the 3 questions will be hard, medium, and easy. And if a person cannot answer those questions, I'll deduct 30 points. That's for exam 1 person. Okay? So I hope I will not do any of it, as it is absolutely not pleasant and useless waste of my time. And the reason I would even consider doing it, you see, I mean, I feel 2 things. Last semester,
Hello.
Mute yourself, guys, if you are talking. Okay, where were we? So the reason I do that, well, several things. I'd say last semester I had, again, a pretty good following. People stayed after class, which is something I want you to do. Anything unclear, stay after class, we discuss the material, anything, right? If you're ashamed to talk before other students, you can talk to me. I hope you think I'm a person that will understand you. But so I tolerate not understanding very easily, but I do not tolerate not wanting to understand. That really upsets me. And the other thing is that it cheapens the entire grade. So there are some people that work very hard, and you see, it bothers me personally if I give those people 70 over people that did nothing and cheated and got 100. So that's one reason I pursue such things. Really, it's completely empty. I have to do one small thing. If you're interested, I'll show you what that small thing is. Let's see, release one of my creatures to freedom. All right. So yes, so let's go back to the material, guys. I hope you are very fresh. I hope you enjoy what we're doing. So again, remember what is the derivative. Before I mention it, would anybody actually like to say it themselves? Especially a person that is not sure what it is, but just has a small inkling, maybe a small light. What is the derivative? What is it about? What does it do? So David says limits. Well, it's a kind of limit, definitely, but that's very vague. It's already kind of, well, what is a derivative? I haven't been thinking about derivatives for the entire weekend. What is it specifically? It is a very, very simple concept, guys. It shows the rate of change, very vague. Right? I mean, you see, if you came to the street, it shows the rate of change. It's very just, what does it describe? If I asked you to describe a giraffe, you would give me a much more lively description, I bet. Kirill, slope at a point, that's beautiful. Slope, that's beautiful. Dragon, right? It is a kind of slope. So here is, you see, if I ask you to explain a giraffe, I think you would say it's an animal that's more or less orange in color with black spots that look like you know, shards of a broken urn, and it has a long neck, and it eats leaves from the tree, right? You can say so much about the giraffe. When you say it's a kind of limit, it's like saying the giraffe is a kind of animal. What sort of a description is it, right? You want to see it perfectly. So here is what the derivative is. From a geometric point, you can zoom on a curve. Very important idea, guys, right? Zoom on a curve, and some curves, when you zoom on top of them, you will see a line. You understand? If you zoom on top of the curve, you will see a line. The derivative is the slope of that line. That's our context. And another way to mention that is to say, well, the derivative represents the slope of the tangent line, which means take a fixed point P and another point Q and slide the point Q towards P. And the distance between them is very small, so it looks like the line goes through only one point, at least locally, like over here. It looks like the line goes through one point alone, and that is the tangent slope. And we mentioned several times why that is important. Good, guys? You see, guys, there are two things. When you don't think about the concept, it's gone out. It's completely gone. So all the effort we placed in it, all the effort I placed in it, is just completely vanished. It's just a futile exercise. Not only that, you're gonna take so many classes in this college, and all those classes, let me be honest with you, useless, right? If you and even if it's a good intelligent class, it's useless unless you think about the material deeply. You either gain this thing, or you pretty much went to college to get a piece of paper. And what you can do with a piece of paper, well, you know, when there is no toilet paper, you know what you can do with it. So we have those two definitions. We have this definition number 1 and definition number 2, which uses H. They are logically exactly the same, but psychologically they give you, they impel you to do a different strategy, to employ a different strategy and calculate the derivative in a slightly different way. And I'm not sure if in this class I finished it or not, I can't remember it anymore. I gave you this example where you had to take the derivative of f using notation 1 and notation 2. And many of you, I'm not sure if you were convinced, many of you, if said anything, you said that notation B is more convenient for this exercise. And you were objectively wrong. What do I mean by objectively wrong? Is that using notation number 1, you are writing fewer symbols. If you're writing fewer symbols, that means that it's much faster that you can carry out this algorithm. Okay, writing more symbols means the algorithm is longer. You know that from programming. The more operations you have to perform, the more you have to write, the slower and less efficient you are at calculating, at finishing your task. Same thing happens here. If you apply the definition using notation 1 for a polynomial, you are using fewer symbols. For not only polynomial, but for any algebraic function, right? I did the calculation using the second formula, a plus h minus f of a over h. And here I expanded the parentheses, and that was pretty many symbols. And here is in my remark, I gave you this rather complicated looking expression, and I just said, could you calculate using the definition of the derivative, what would that be? So if you use notation 1, the number of symbols used to just write the definition up was 33 symbols. If you use notation 2, the number of symbols you used has already been 43, 10 more symbols. And once you expand the fourth power, it would be even more symbols. So it would be unwieldy, it would be long, it would be difficult for you to write it in one line. And with each time you write this formula, you write at least 10 extra steps. And so you have 10 plus 10 plus 10, you write it 3 times, it's 30 extra symbols that you have written. And not to mention that when you make the expansion, you cannot just grab the entire formula in your eyes. So notation 2 is always better for, notation 1, I'm sorry, is always better for all algebraic functions, which means I would have never used notation 2 for any of the expressions we have considered thus far. All right. So another thing is about considering about this problem is notice that when I take the derivative at some point a, so for example, if I pick my function x squared, the derivative at some point a, you can calculate it, happens to be 2a. And if I do the same thing for root of x, the derivative happens to be 1 over 2a. I switch from x to a. There are moments where you would like the derivative function to not be a function of a new variable, but to stay a function of x. Good? So we would say we would modify definitions 1 and 2 to allow us to use the definition and not switch to another letter. And here is definition 1. I use another letter z. It doesn't matter what you use over here. It cannot be x. So x takes the role of a in the previous point, and that x means just the point at which we are zooming on the curve. So z going to x, f of z minus f of x over z minus x. So we have the fixed point, the p point is x comma f of x, and the moving point q is z comma f of z. So before I move on, I was speaking and you were all silent. Could you please spell in your chat, tell me yes or Y or something, so that I know that we can proceed. Everything I said thus far is clear. Please do that. Or ask me a question. Yes, Dragon, thank you. So I'll repeat the Z part. Again, guys, a lot of you, and that, by the way, happens not only in mathematics, right? A lot of you are nominalists. So, for example, you hear somebody say something that's not politically correct, and you might be getting upset. And why do you get upset? One reason for it is you believe that what a person is saying is what a person is. That's called nominalism, right? So let's say if I say, I love children, right? I really care about children. And you say, oh my God, he's such a wonderful person. But words are not deeds. So you're nominalists. Many people I notice, and I'm not sure you are, right? Are nominalists in mathematics as they are nominalists in real life. What I would like you to be is not that. I would like you to look at an expression and think about what it means, okay? So when I look at it, I don't see X or Z or any things like that. I just translate what is the meaning of it. Like, for example, when I read the word then, I don't see T, H, E, and N. I just see some sort of meaning out of it, right? I just grasp it. Corresponding, I don't see C, O, double R, and whatnot, right? I see the meaning. Similarly here, what's the meaning here? The meaning is that we picked 2 points. What's the fixed point? The fixed point in this case is, well, not the fixed point, the point of attention, to be precise. I called it point P, the point at which I want to find the tangent line. It has coordinates x, f of x. And the other point that I need to calculate slope, you understand why we have this expression. We need 2 points. 2 points represent a line. Using 2 points, I can calculate slope. But I want the second point to melt into the first point, thereby creating a tangent line. That's very simple, correct, guys? You can see that, right? 2 points that are very close together are like 1 point. So you use this idea. There are 2 points truly, but like 1 point. So z, f of z is that other point, and it's a movable point, right? It's really, it's not going to be around. This is just something very close to x. Or using definition 2, what we have is we represent that second point as just a perturbation. You see, this is in the denominator, it's the difference of the x coordinates of the point, but I represent that point as imperfect x. So here I don't use a different symbol. I'm just saying essentially that my x coordinate of that second point, the imposter x, is very similar to it. It's just actual x plus the impurity, which is called a perturbation. Good. And that impurity goes to zero. You understand that I don't even need to do too much to understand that those are synonymous expressions. You understand? Here h goes to zero, here z goes to x. Doesn't matter what's happening here. We have one point that's an imperfect imitation of x, of that point at which I'm zooming in, and we are merging them together. Same thing is happening in both 1 and 2. So here is your task, guys. Let's see how fast you can do that. Here is my function, and you can use whichever notation you feel is best. I want you to find the derivative of this function using the definition. Copy this question, guys. I want to open another window possibly to show you something short afterwards. Okay, you copied it, correct? I'm gonna look through my website. Okay. Okay, Kirill, that's good. Dragon, you are forgetting. You are forgetting the root. Alexa. Yeah, well, don't worry, guys. If you are stuck, what you do sometimes. Here is my advice, right? If you get stuck when you are doing it at home, I mean, I'm giving you just a few minutes here. When you're doing it at home, leave the problem alone, return to it, right? Actually, do the same calculation several times. Okay, so and just from scratch, because when you understand it efficiently, it is very quick what you are going to do. All right, let's go through the question together, guys, and practice solving it. Practice solving lots of such questions. It trains your ability to just do basic algebra, and it trains your recognition device. Okay, so here is the formula I employ. I will employ formula 1 because this is an algebraic function. For algebraic functions, I found, and I've tried to explain to you above, through experience, that formula 1 is much better. You can do it with formula, yes, Dragon, beautiful. Except it's not 9 over x, it's 9 minus x in the root. But yes, I think it's some sort of small mistake. There are a few things there. So here, guys, what I do. Yeah. Here is what I do. You see this line? Now it still looks complicated. So first of all, do I need to re-explain anything here? I just set it up. I just take f of z minus f of x. And z is this dummy variable. It disappears. It's the sliding point. It's the x coordinate of the sliding point, q. In my drawing over there, it's q. Yes? So then I group like to like. Z squared minus x squared, like to like. If you stay in office hours, we can practice a few of those questions, right? We will train to do them very fast. Like to like, and then I isolate. Look at it, z squared minus x squared over z minus x. I can deal with it separately. I recognize this. Now I have the root of, I have the 3 root 9 minus z and 3 root 9 minus x. I group it together, factor the 3, and I have this expression. So far, so good? And then I begin dealing with each side separately. This here, again, the main problem, the main struggle is factoring so that denominator can be cancelled. So z squared minus x squared, I factor it to z plus x, z minus x. I can then cross away z minus x. And here on the other side, I see root minus root, I multiply by root plus root. That's called multiplying by the conjugate. So I do that for the numerator and denominator because I'm not allowed to change my expression, right? I just multiply this way by 1. Everybody understands why I multiply by the conjugate? It's like a minus b, a plus b, it will be a squared minus b squared. Great. Now, once we push on this limit here, I'm just dealing with that left part. Z going to x. Now it's like adding the same number x to itself, so it becomes 2x. So this part is easily 2x. So I have 2x plus, and now what do we have here? Again, don't forget to put parentheses. Some people might not write the parentheses around 9 minus x, and that will be a mistake. Habits, guys, are very hard to change, and some of you, when you struggle, you might feel that you're not improving, but improvement happens gradually. It's very important, therefore, to practice quite a lot. Yes, Ibad, why 2x? Because look at this expression, right? I was able to factor z squared minus x squared into z plus x, z minus x, and in factored form, I can cancel out the denominator. So it's not there, right? Because z is not x. I'm not multiplying and dividing by 0. I can cancel it out. And I have now z plus x. But z is going to x, which means I'm essentially adding the same value x to itself. And therefore, I have 2x. It's like x plus x now. Do you understand what z is? Z is an imperfect x. An imperfect x plus an actual x will look like x plus x, or like 2x. Now, do we see what we have here? On the numerator, I have 9 minus z minus 9 minus x. And again, guys, algebra, every step here is just algebra, right? If when you make a mistake like that, that's because you know, you haven't been training with it. So 9s go out. We have minus z plus x, which is the same as minus z minus x. And I do not multiply anything in the denominator. Don't ever, you see, guys, some of you, on the one hand, you don't like to spend extra effort. On the other hand, you spend it exactly where it's useless. So if you were to multiply it through the denominator, it's the equivalent of going up the stairs and then going down the stairs, right? You're being inefficient. You're doing one action that you don't have to carry. Always do the minimum action that you have to solve a problem, and don't bother with everything else. Right? So I left it alone. There was no interest for me to multiply anything in the denominator, because again, why did I multiply by the conjugate? It's only for the numerator that I wanted it. Agreed? The denominator was my payment. So then I can cancel it out. Look at it, I cancel it out, so there is a minus here. And now I can push z to x. Now what happens here? It's root of 9 minus x plus root of 9 minus x. That's how I get on the denominator 2 root 9 minus x. And this 3 times minus 1 is where I have the minus 3. This is my solution. Are you following me, guys? So write yes if you understood my explanation. And again, I do hope that you will stay after class to practice a few problems. Definitely, if something is not clear. Definitely, you should have questions for me. If you solved exercises, you can just say, do we solve it this way or that? Okay. Okay. The third step, do you mean, what's the third step? Is this here, this step, or is it the very last one, right? What do you say, what do you consider third step here? So, Stephen Lin, is this the third step? Or is this the third step? Well, I'll go from here. So what do you have here, right? Do you understand how I, in the second line, I just get minus z minus x, yes? And on the denominator, I touch nothing. So I can cross out, you see there is a multiplication here, I can cross out z minus x. So now it's not there. Good? It's not, so I just factor out minus 1. Do you see that? Minus z plus x, it's really minus z in parentheses minus x. Good. You see the step, guys. Yes. You also are guided somewhat by the knowledge that you should get in the numerator something that cancels z minus x. If you cannot cancel it, then the derivative will not exist. So you cancel it out. Z approaches x, root of, and it becomes root of. Look at it here. Z is now essentially, there is a 1 here. This is gone. So this essentially becomes root 9 minus x plus root 9 minus x, because z is close to x. So denominator looks like 2 root 9 minus x. I didn't carry 3 into minus 1, and I have minus 3 over this expression. And therefore I'm done. Good. And now we are going to observe. And here is the thing, guys. I know that some of you, and you can talk to me, by the way. See, one thing is people hold their tongue. So some people might know calculus from before, or at least have studied it from before, or you have a way somehow that gives you the solution rather quickly. And then you wonder, and some people write that, and I find it very curious. They say that I make things more complicated sometimes, or I overcomplicate things. If you think so, you can tell me, and we can discuss why I do what I do. Okay, guys, what I'm trying to show you is, first of all, I'm not teaching you this material so that you just pass this class. I am hoping very much that you will continue with this material, or that you will know it for the rest of your life. And that actually happens with only a few people. So many people get an A, but very few people deserve that A truly, right? That they truly understood something. And to truly understand something, for example, you might know shortcuts. Why am I making you go through such formulas? Very simply, guys, here is an introduction to mechanics. It is an advanced introduction at MIT. And MIT students, many of them flunk this course. It's extremely difficult, okay? And why is it extremely difficult? Because it's physics. What calculus is useful for, one of its great applications is physics, okay? And when you do physics, you're not going to be asked to find the derivative of such and such function. No, by the time you are at the derivative step, you solve the problem. Understand? I mean, that thing that we are doing, it's already you solve the problem. The main difficulty is setting it up. You see, you are observing an actual phenomena, and no, not something that is in your textbook exercise, find the derivative, add 2 plus 2. No, you're observing an actual phenomena, and you try to describe what's happening to that system, you see. So, and then you begin setting up, I do it in slightly different notation, you begin setting up formulas, and then you have some derivative equal to some other derivative. You have a differential equation of sorts, okay? You come up with formulas on your own, and when you solve them, it ends up, you see, look at it. You see what I'm saying? You can see that this t plus delta t, that's your h. It's your second definition that they are using over here, okay? You come up with your own formulas, and then you realize what they are, what they represent, and then you're able to solve it, right? I'm trying to teach you to think calculus, not to solve some stupid problem like this one, right? This is not an interesting problem at all. It's just, you know, what do I care about it? I can solve it in 10 different ways. I want to teach you what the derivative is and what you can do with it and how to use it as actively as you possibly can. I hope you see my point, and I hope you agree with that philosophy, and you can definitely talk to me. I'm happy to hear if you have other perspectives. So here is my question, right? So we are talking now about the relationship between the graphs of y equals f of x and y equals f prime x. And one thing that that you have, you know, it's very, even today you hear about flat earthers, right? You have people that maintain that the earth is flat. And some of you, of course, they go, haha, what stupid people. Funny enough, do you know that the earth is round? Can you prove that? Right? Because if not, then you are holding a belief. If yes, if you study physics, if you study, or you have some argument that the earth is a sphere, then you know it. Okay? But it's pretty curious that many people that care not about physics, there is a picture dragon, but that's a funny thing. I can draw you a picture of earth on a cube. So why is that a proof? That's not the way people figured it out. You understand that the amazing thing is that that it was known many years before photographs were available, before any of it could be done, that the Earth is a sphere. Not quite a sphere; it's an ellipsoid. How was it possibly known? That's a complicated question. You understand? People just figured it out by thinking, not by seeing it. Right? You might have been in an airplane, looked out of the window, and if the airplane is high enough and it's not cloudy, perhaps you noticed that the Earth is curving. Perhaps you have noticed that, but still, you know that there are many people. Many people do not fly, or I'm not sure exactly, but they're still obsessed about Earth being flat. At least it used to be something in 2017. I'm not sure how much it is a thing today. But why, for so many years, so many people believed that the Earth is flat? Would anybody like to tell me? What do you think? Why for so many years people believe the Earth is flat? And by the way, you know, most of you believe the Earth is round. In other words, you see, you are not better than the people that believe the Earth is flat because you don't know it. You just believe in another thing that somebody else told you to believe. So my question is, why would so many people for so long think that the Earth is flat? What do you think? What is it that those people somehow understood but did not, well, did not understand, sense, but did not know what it is, did not spell it out? Well, the reason, guys, any ideas? Well, they actually here they did know calculus naturally, but in some sense, they did know calculus very well. You know why you think the Earth is flat? Because people are observing the derivative. Exactly what we do here with the derivative, right? You take a sphere, and if you zoom on a sphere locally, it will look like a plane. Just like when you zoom on a curve, it looks locally like a line. Do you get it, guys? So if you have a huge sphere, zoom in at its surface, and it will look like a flat plane. You cannot tell apart the sphere from a flat plane. So they were doing calculus without realizing it. And now comes this difficult part, which I hope I will explain. I'm terrified because I don't know what you imagine, right? So my question is, if a curve is differentiable, right? I'm trying to explain to you how would I know such a thing, right? With calculus, if a curve is differentiable, how do I know that when I zoom in at that curve, what I will be seeing is a line? How do I know that? Differentiable, it means that I can find the slope of a tangent line. I can take one point and another point Q, slide it to point P, and I can calculate the slope. Why would that tell me that when I zoom in on the curve, it looks like a line? In higher dimensions, when I zoom on a surface, it looks like a plane. You understand? The plane is like a two-dimensional line. Are you with me, guys? Yes? Or you see, I'm afraid to overclock your graphic card. Right? It's always a big fear of mine. So tell me when you need to, when the steam is coming off your ears, and I know that you are following me. I am asking you, how do I know that when a curve is differentiable, it's like a one-dimensional analog of this flat Earth thing, that it looks flat when I zoom in on that curve? How do I know that? Does my question, first of all, make sense to you? When I say a curve is differentiable, what do I mean? Anybody? When I say this curve is differentiable, right? If it means nothing, then how can you answer this question? Oh, Kirill, you have a twin.
Yeah, sorry, Professor.
Why sorry? It was interesting. Guys, my question, does it make sense to you? Lakey, wonderful. It means you can find tangent to the curve, precisely. In other words, the limit will exist, etc. That's beautiful. So I guess I will not keep you in suspense, and I will talk about it, okay? At least how I understood it. So my question again, guys, I hope you process my question, right? And if you understand derivatives, you should process this phenomena pretty well. I'm asking, okay, we have this concept, we can find a tangent to the curve. We kind of develop this technique of finding tangent to the curve. We pick one point, we pick another point, slide that other point, and if that results in a line, then we have a tangent to the curve. Why does it mean that this curve is locally flat? Locally like a straight line. You zoom in, like you are landing on Earth, it looks, I mean, if it were a perfect sphere, Earth is not a perfect sphere. If Earth were a perfect sphere, you would zoom in at any point and you would think you are on a plane. Do you understand what I'm saying? You would actually, if you live there forever, your first theory might be that the planet is flat, as it has been for many years. It was considered flat. Why that would be the case? So here is, I'll try to explain to you. Say I drew you this bouquet of flowers, okay? So imagine you have this landscape, okay? When you look at this landscape and you are standing at point P, you can draw a bouquet of flowers. You see, which means any line that goes through point P and one other line through the curve. Do you agree? You have this bouquet of flowers. I just drew a few of them, but it's actually many, many more flowers that you can draw through this point. All of them. Good? Are you with me, guys? You look bewildered, at least to the people that I can see their faces. It's not, guys, everything when you think intuitively, it's the entire material is just extremely clear. You see, you think geometrically in terms of pictures. So it's a bouquet of flowers. Now this is the bouquet of flowers as it looks under a particular zoom. Now imagine I make the zoom, I zoom at the point P. So that means that my horizon is becoming narrower around the point P. Here is a line where it's narrower. You see, I cut those pieces, and now I have this purple bouquet of flowers. And what do you notice about the purple bouquet of flowers? Here is what I try to show. You see, this red hourglass shape is the bouquet of flowers, all the flowers that you notice when you are around the red ridges. And if you are zooming in near P, then you are truncating the curve. In other words, you stop seeing this part of the curve, you stop seeing this part of the curve, and the hourglass gets narrower. The bouquet of flowers get less fuzzy, they get more focused into one line. Do you understand? This bouquet of lines, they are at a much sharper angle to each other, and that would actually tend to this fuzziness will tend to zero. In other words, it will tend to one particular line. Why is that the case? Because think about it. Any point that I select for the other point on the line is a possible point Q. It could be either selected here or here. I select another point Q, and you know that the slope of the tangent line must converge to, there must be a number that we get there. You agree? So when I narrow my perspective around P, I am also narrowing X closer to the point A, which means that the ratio f of X minus f of A over X minus A, the slope ratio must tend to one number, which means that those lines must merge to one line. Do you understand? And vice versa, when lines merge to one line, that will be the tangent line. You understand? Geometrically, there is no difference. The tangent line is that, or the tangent plane, if you're thinking about planet Earth, is your, it's called local linearization. It's what the world looks to you locally if you're a very small creature. And it's extremely convincing, and you understand, think about it, right? People imagine that the Earth is a flat, you know, you have mountains on it, but essentially imagine that it's the mountains are lying on a plane. You follow, guys? So for many years, this phenomenon of calculus was observed. It just was not understood what it is. And that's not, and that's a very, very useful type of idea, right? So in other words, here is what I'm trying to tell you guys. When you are zooming in on a curve at the point A, the curve will look like the tangent line. Are you following me? You zoom in, and you will eventually not be able, under high enough zoom, you will not be able to tell whether it's the tangent line, whether it's a particular line, in other words, or whether the curve is curving. And if you are clever, you can use this idea to know what is the derivative at a glance. Okay, let's so yes, David, wonderful. You zoom in on a particular point, and here is what I'm saying. From a geometric, it's called, there is an entire branch called differential geometry. It's a very complicated branch, and it studies the property of geometric shapes in terms of derivatives. From the perspective of differential geometry, what it means for a surface to be differentiable is that when you zoom in on the surface, it looks like a plane. And for our purpose, we are dealing with curves. Zoom in on a curve, it would look like a line. There is no difference. So if that happens, then the function is differentiable. And yes. And if that does not happen, then the derivative will not exist. So if you're clever, you can use those ideas instantly, guys, instantly to figure many properties of differentiable curves. So here is my first question. Let's do it intuitively, and we'll do it formally as well, right? So if f of x is differentiable at the point A, then the function is continuous at point A. How do I know that? Would anybody like to tell me how I know that? You see, so this should not be a surprising result at all. Guys, tell me, remember what is continuity, right? So let's talk together, right? Don't stare at me. Simply, just what is continuity? In very simple words, right? A function is continuous means that what? It is infinity, so that's very metaphysical, and no, that's not continuity at all. No hole in it. Yes, no hole in it, right? So in it, to be precise, this is what it means. That's the definition, but the definition is supposed to capture a concept that you can describe in words. So here, guys, let me remind you what continuity is. You take a function and you graph. You create a graph for it, and the graph looks like a wire. Good. A graph looks like a sort of twisted wire. Now that wire is continuous if it has no holes or if it is not torn apart, which in terms of limit means that limit from left is limit from the right. That's what I do with the figures. You see, look at it. I slide along my invisible curve. I slide my fingers and they merge in the same location anywhere at any point where I slide my fingers to. And when the fingers merge, it's fused. You see, this point is filled. So that's how it's defined. And differentiable means at any point there is a derivative. Yes. Now my question is why having the property of differentiability immediately implies that we are dealing with a continuous function. Very simple question if you understood what I said before. I think one person was already in the comments suggesting the right reasoning. Come on, guys, imagination, right? You are flying onto this curve, closer and closer and closer. What do you see? You said the curve is differentiable at the point A. I am flying to point A, f of A, that's my coordinate. I'm zooming in at it. I'm a small creature compared to that curve, and I'm landing there. What will I begin to see? What shape? When you say has limit, whatever, it's like the eyes are not there. What shape are you seeing? Well, curve. Well, sure, it will be initially it's some sort of curve. Y equals f of x is a sort of curve. David Wang, wonderful, right? You begin differentiability. That's what I just said before, guys. You are zooming in, and it has the property of you're seeing the line. Do you understand that or not, guys? Right? It's very visual to me. I'm not sure what happens there. I imagine this curve. I can even imagine a color if you want to, right? What color do you imagine when you zoom out on a curve? Not that color matters here. So I'm zooming in at it, and then I stare at it, and I see, my God, it looks like a straight line. Now, why does it help me understand why the function is continuous at that point? If it's a straight line, then it's what in particular? A straight line is a connected shape. Isn't it easy, right? It's a connected shape. So I zoom in, the curve maybe looks like this. I zoom in, zoom in, zoom in. It looks like this straight line. It's a connected shape. That's it, right? I know it's continuous. Lines are obviously connected objects, so it's continuous. But of course, we always provide a formal explanation just to be safe. But you understand? I mean, if you have an intuition, if you walk in the forest, right, and you have no dead reckoning, you know what would happen? If it's a big enough forest, you will return to the same place you started with. One leg is stronger, you will make a circle. Have you known that phenomena, guys? It's true. You walk in the forest and you come back to where you start from. You're not going to get out of it. You're going to walk in circles. You're just going to make a big circle. So why does it happen? Because you have no idea where you're walking, right? You're exactly same thing in this material. You're exactly where you start because you have no dead reckoning. You're not trying to say, well, here is a feature. I recognize this feature. I understand it. And that's where I walk. Good. So here is the argument formally, guys, right? So first of all, formally, the function being continuous at a means that I have to verify that this limit as x goes to a of f of x is f of a, that I can plug a here, right? But I do not know much about this limit. By the hypothesis, I am told the function is differentiable. So this limit equals to f prime. This limit exists, correct? This limit exists. So I want to then translate. That's what I call being guided by it. You see, look at what I mean by knowing where I want to go. I want to go from this limit to something in terms of this limit because I know something about it. You follow me, guys? So I begin limit as x goes to a of f of x. What is that? Well, I need to construct this structure. So it will be f of a plus f of x minus f of a. You understand? Everything that I do, this is my payment. This is what I want because I want the numerator here. And then the next thing I do is I divide and multiply by x minus a. Look at it. Do you see this expression? It's exactly the same as I had before. And now the limit as x goes to a of f of a is just f of a. And now the limit of this part here is the derivative, and the limit of that part is 0. Limit of a product is the product of the limit. So I have f of a plus f prime a times 0 equals f of a. So I concluded, look at it, I concluded formally that the function is continuous at the point a. So here is the next question. I'm not sure, guys, how bewildered you are, but let's see. Differentiability implies continuity. We understood why? Without the formulas, because differentiability means that I can actually know something about the shape of my curve. Not global shape, but zoom anywhere locally. Maybe here is my curve. I zoom in, zoom in, zoom in, zoom in, zoom in, and it begins to look like a straight line. You see me in the video? The curve from a distance maybe locally looks like this. I zoomed in, zoomed in, zoomed in, zoomed in, zoomed in, and I see a straight line. And differentiable at every point means that no matter where I decide to land my little spaceship, I will see some straight line. It might not be the same shape. Maybe some other place in the curve it looks like this, right? So I zoom in, zoom in, zoom in, zoom in, zoom in, zoom in, and it looks like a straight line, a different straight line. But straight lines are connected pieces of curve. So the entire curve at any location is connected. And this was a formal verification using the definition of continuity and the definition of the derivative. Now, my question is this. Differentiability, so does continuity imply differentiability? What do you think? So if I know that my function is continuous, will I also know it's differentiable? What am I asking? Will anybody translate it into a very simple language? And then when I say continuity, differentiability, if you don't understand what those words mean, they are big words, then the discussion is meaningless. Gabriel, are you here, by the way? Gabriel G. Great. Yes, but I'm asking you that if we have a continuous function, does it also mean it's a differentiable function? But I use the word continuous and differentiable. What am I asking in terms of a movie? Let me ask you this way, guys. So you see, you don't describe it with very active words. So I'm not sure what process you process. When I ask you verify whether that particular curve is differentiable, what are you going to do? Let's say imagine that there is some sort of cosmic curve there, and you have a spaceship. How would you verify that this curve is differentiable? You're like a little fly over there, right? What do you do? Bzzz. What do you do? Yes, Stephen. In essence, yes. What you try to do is, I ask you, verify. Let me show you basically using a drawing to be sure, right? So imagine that I ask you here. I draw you a picture. Here is a picture, and I say, could you please verify whether or not the curve is differentiable here? Right? What do you do? So if you're very small compared to that curve, you're that insect, you're going to go bzzz, you're gonna fly closer and closer into this point, and you will try to land there and tell me what you observe. If you begin observing a straight line, it looks like, for example, as you're zooming in, it looks like you would observe some straight line that looks like this. If you zoomed in very, very far into the curve, it looks like that's what you would be observing, right? You're not like this, you're already a point, truly, right? It would look like you're observing a point. That's what it means to be differentiable. Good? And anywhere else you zoom in, if it's another point, it's differentiable at another point. So for example, if I asked you to zoom over here, here is the line that you would observe. You see, I drew this line over here. When you zoom in, that would be what you see. So I'm asking you now, it's slightly more complicated here, right? So I'm asking you, if you were to, my God, where did you all go? Oh, everyone disappeared from me. I'm asking you, if you will zoom in on a continuous curve, will you find what? Just a continuous curve. I'm asking, what will you find that it looks like a straight line? Who exactly? Will it look like a straight line if it's just an arbitrary continuous curve? That's the question. Guys, can you hear me? I'm in total blackness here. So Stephen thinks that when you zoom in on an arbitrary continuous curve, it will eventually start looking like a straight line, and therefore every continuous curve is differentiable. How many of you agree with Stephen? Definitely Stephen understood my question, which is very good. What about the rest of you? Oh, here you are. Irvin agrees. What about the rest of you? Makes sense, says Dragon. You understand my question, guys, right? So everybody sees it. You see, I visualize it somewhere in here. So there's the graphic card, right? So it's not pitch blackness for me. I do not know what I'm zooming in, but I see some sort of curve. So I'm going with my spaceship closer and closer at the point of this curve. And I know, I'm told somewhere there is something I verify, the curve is continuous. Can I be sure that when I zoom in, locally it looks like a straight line? So Ibad says yes if you're zooming in. Guys, you all saw this definition of the differential, this geometric idea of differentiability. Geometrically, a curve is differentiable when, if and only if when you zoom in it, it looks like a straight line. That's what I try to explain with a bouquet of flowers. So, so far, everybody that answered, they agree that every continuous curve also is differentiable. In other words, if a curve is continuous, I zoom in, it looks like a straight line, under high enough zoom. Well, Ibad, in general, you're talking about first we have to be clear about what you mean is a curve. So there are some curves that are not functions of the x-axis. So for example, something like this is not a function of the x-axis, but it's a differentiable curve because, let's see. So zoom in at this point, for example, and you see, I think you see this tangent line. You see, if this thing were to, if this small region were to occupy your full screen, it would look like the continuation of this line. So this is this picture that I drew is an example of a differentiable curve, but one that's not generated by a function of the x-axis. Well, Ping, not sure, right? That's what you are saying. I'm not saying that. I only heard from what, 3 people, guys. What about the rest of you? No idea? I bet you have not been to the New York Aquarium in a long time. Maybe never. Have you been to the New York Aquarium? Well, but you have been to some other aquariums, right? Or you never saw fish? I was very impressed when I first saw those creatures. There is an aquarium. I mean, it's already there is an. I'm not sure, guys, what you have been doing here in New York. How long have you been here? I actually used to work in one. That makes sense, Irvin. So you haven't seen much. Although the aquarium is less interesting now than it used to be. Fewer creatures and yeah. Here is asking the question in another way. Again, I mentioned it already several times. Continuous means that you zoom in on the curve and it looks like a whole curve locally. Differentiable means what? Differentiable means that you zoom in, it looks like a straight line. And the answer, when we imagine that very clearly, the answer is obviously no. Here is a basic example. Look at this thing. I will explain later what does it have to do with aquarium. You see this? Imagine that I have this broken line here and I zoom in at the peak. No matter how much I zoom at the peak, it would look like the same shape. It would continue looking sharp. Do you agree? Zoom in more and more and more, and we can actually give, I will see if I do it below, it will always look sharp. It does not ever look like a straight line at the top, because you see something going down, something going up. No matter how you zoom in, that's pretty clear intuitively. That already tells you that continuity is more general than differentiability. Differentiability implies continuity. You cannot be differentiable and not continuous, because continuous means you're a whole curve. So it means that, right? So if it's differentiable means not only that you're a whole curve, but locally you look like a line. So when you imagine differentiable functions, imagine a chain of microscopic line segments. You understand? So you can imagine a chain of microscopic line segments. Everywhere you land looks like a some segment of a line. And there are also, so differentiable curves, they are called smooth curves. They're pleasant to the touch, they don't cut you. You see this place, it's sharp, it can cut you, but the differentiable curve will not cut you. Here is an example of a much worse type of non-differentiability. It's called a cusp. And what's interesting about the cusp, you can see that the sharpness can be measured as this angle here. But this cusp, you can see there is a point here, and the angle here gets smaller. You understand? The angle here is not staying the same. Here the angle is, I don't know what the angle is, let's say 30 degrees. Here the angle is getting smaller, so that's extremely sharp. And that would be a worse type of non-differentiability than the picture of the triangular curve. Yes, but at that sharp point, it is continuous and not differentiable. But if you zoom in, if you zoom in on the left side or on the right side of this point, it will look like a straight line. So it's differentiable here, but not differentiable at the peak. Similarly, here at this peak, at this cusp, the curve is not differentiable. No matter how much you zoom in, it will not look like a straight line. And this is actually even worse, because this is somewhat sharp, this is extremely sharp. Okay, because the blade here is you see, you don't keep the same angle, you're actually making the angle thinner. You see, so I mentioned observe it's everywhere continuous. How are you observing it? It's everywhere a line. You can zoom in this point. You can clearly see that the points of the, so you see, you zoom in here, move to this point from left or from the right, the pieces of the curve, they emerge in the same location. And this function, by the way, is defined. So look at this function, it's piecewise linear. It's defined to be 1 plus x if x is smaller than 0, and 1 minus x if x is bigger than or equal to 0. This is my my function here. It's really giving you the formula for this type of shape. That formula is 1 minus absolute value of x. Good? Well, I will not solve this question just now, as I think our time is over. So what I would like to ask you is, of course, some of you have questions, I'm sure, or should have questions if you opened the book or solved anything. So we can discuss those questions, or we can solve, we can practice derivatives, or yeah, any of that sort. So I'll stop this recording.